In the quiet space behind the terminal, the South Asian male engineer stood observing the matte gray metallic aircraft body. The workers aged 22 to 25 worked in silence, every movement as precise as if programmed beforehand.
The narrow-body aircraft lay there without haste, without displaying power, yet radiating an almost absolute sense of stability.
There was no roaring sound or sign of speed, only a quiet balance covering the entire space. That created a clear contradiction with what people usually expect from a machine flying in the sky. Why would a vehicle designed for speed not place speed as its highest priority?
That question existed not only on the aircraft body, but also in the way engineers observed and inspected every detail.
The aerodynamics here match the schematic perfectly.
What about the stress points near the joint?
And in that silence, the central question began to form more clearly than ever. Under normal operation, every civilian flight requires an almost absolute level of stability to ensure a smooth journey.
The female engineer checked the connection points on the wing, where lift forces are evenly distributed every second of flight.
The workers continued tightening each component, neither faster nor slower, only following the established rhythm of the process. A civilian aircraft does not simply fly, it must fly in a predictable manner under all conditions. Calibration complete. Check the boundary levels.
Confirmed. All systems show green and stable. The male engineer stepped back, seeing the structure as a fully balanced system from start to finish. Speed is not ignored, but it is never allowed to disrupt that stability.
On every flight, hundreds of passengers rely on that stability to feel safe. Every vibration, every small change can be clearly felt within the confined cabin space.
And therefore, stability is not just a technical choice, but an absolute requirement.
But that itself raises a deeper question about the nature of civilian aircraft design.
Why not create an aircraft that is both faster and equally stable as desired?
The faster the speed, the greater the force acting on the structure, and the harder it becomes to control linearly.
The workers stood behind, understanding that every small change carries a chain of complex consequences. The male engineer gently touched the metallic surface, as if feeling the invisible pressure it endures during flight. High speed is not only an engine issue, but a problem of control and system response. The faster an aircraft moves, the more sensitive it becomes to environmental disturbances. This creates a contradiction between the desire for speed and the need for absolute control.
And that contradiction becomes the starting point of the answer.
The core reason lies in how safety is defined in civilian aviation.
These parameters are critical. Temperature must hold steady at 45, pressure at 150. Zero tolerance.
Got it. 45 and 150. Every detail matters. Let's double check the hydraulic lines here before we sign off on this section.
Agreed. The structural integrity looks good, but let's be thorough.
A civilian aircraft must never behave unpredictably in response to its environment.
Stability allows pilots to predict the aircraft's behavior in all situations.
It reduces risks from external factors, such as turbulence or pressure changes.
The workers completed a step and stepped back, leaving a structure that had been verified as safe. High speed may reduce travel time, but it increases the complexity of control.
In a system carrying hundreds of people, that complexity must never exceed control.
Therefore, stability is not a weaker choice, but a smarter one.
When compared directly, combat aircraft accept instability to achieve maximum agility.
We've minimized the joints here for better aerodynamics.
I see. It's a stark contrast to the aggressive designs we're used to seeing built with such heavy machinery.
Combat aircraft can react quickly and change direction abruptly, but require far more complex control systems.
The wing design here is optimized for stability rather than flexibility.
Civilian aircraft do not perform sharp maneuvers, but maintain smooth trajectories.
Every worker action reflects priority for precision and balance.
Speed in combat aircraft is tactical, while in civilian aircraft it is merely a means.
Stability reduces structural wear and extends aircraft lifespan.
It also reduces fuel consumption over long, continuous flights.
Ultimately, it creates a flight experience where passengers barely notice the complexity behind it.
The answer to why civilian aircraft prioritize stability over speed lies in their fundamental purpose. The efficiency metrics look solid for this shift.
Yes, the staggered exit improved the flow by 15%.
A civilian aircraft does not need to be the fastest, but the most reliable.
Stability does not reduce speed's value, but redefines how it is used. It turns speed into a factor that serves safety rather than risk. In civilian aviation, every design decision ultimately protects human life.
When protection is the goal, stability always surpasses speed.
That is not just a technical choice, but a design philosophy built on responsibility.